Hello, physical systems or applied physics. Uh, so this is a video lecture for the conservation of energy, and we'll be going over potential energy and kinetic energy. So we'll start with potential energy here. So, or it's also called gravitational potential energy because it has everything to do with gravity. So when we were studying forces, we learned that gravity is a force that attracts two things with mass. And when we're talking about gravity, we're usually talking about gravity between an object and the Earth. So, for example, on the right side here, we got some kind of well-dressed man, and here's the Earth, and the man is going to fall towards the Earth because the two masses, the mass of the Earth and the mass of the man, are attracted, which makes it look like the man falls to the Earth. And when we say gravitational potential energy, so if you guys remember, potential energy means stored energy. So when the man is above the Earth, he has stored energy in the form of gravitational potential energy. What all this means is that we say he has the potential to fall. So if he has the potential to fall, he has the potential to release that energy. We call that a potential energy or a gravitational potential. Basically, what you need to know is that if something has a height above the ground, then it has potential energy because it can fall. And the way that we calculate this is potential energy is equal to mass times a gravitational constant, which is g times height. That g there is actually acceleration. So g equals 9.8 meters per second squared. That is the acceleration that all objects fall toward the ground, regardless of their mass, which is something we already went over. So that g is used in this gravitational potential energy because, and of course, if you're on a different planet, your potential energy would be different. So if this guy was above the surface of the moon, he wouldn't have as much energy to release because he would have a much softer landing because of the lower gravity. But here on Earth, there's the gravitational acceleration is 9.8 meters per second squared. And so with that acceleration would tell you, if you have that acceleration and his mass and the height, it would tell you exactly how much potential energy he has above the ground. So let's do an example together. A pot of flowers that weighs 5 kilograms is on a shelf 1.7 meters above the ground. What is the potential energy of the pot of flowers? Oops. And so let's just do a quick drawing here. So we have our pot of flowers is on a shelf. I'll draw some. I'm just going to draw some grass because I'm using a screen and I'm not good at drawing that stuff. Okay, so we know that it has, oh goodness. We know that there is some height above the ground here. We know that height is equal to 1.7 meters. And we know that the mass of the flowers is equal to 5 kilograms. Okay. And we're looking for, the question is asking, well, what is the potential energy? So that's what we need to calculate. So potential energy, here's our formula right here, is mass times gravity times height. I'll say gravity, I should say G. So remember that G is equal to 9.8 meters per second squared. So what we need to do is you just need to multiply those 5 values. We have I'm going to abbreviate a little bit here, 5 kilograms times 9.8 meters per second squared times 1.7. So if we multiply the 5 times 9.8 times 1.7, excuse me while I go fetch my calculator. Oh. Excuse me again while I go fetch my calculator. I bet you didn't expect me to have technical difficulties, did you? Here we go. There we are. There's my calculator. Okay, sorry. So 5 times 9.8. I hope you beat me to the answer by this point. Times 1.7 is I get 83.3. So with significant digits, that's 83. And the unit we're using here is joules, or I can just put J. So that's how I would solve that problem. And then yep, the answer is 83 joules. So that's how I calculate potential energy. Next kind of energy is kinetic energy. Kinetic energy are just objects that are in motion. And our formula we use for that is 1/2 times the mass times the velocity squared. So remember, velocity is speed plus direction. So anything with speed and mass has kinetic energy, and any object you can imagine has mass. So as long as that object is moving, it has some kinetic energy. And so if you just think of yourself getting hit by something that's moving, whether it's a bee or a car or something, whatever, whenever an object hits you, you can feel it, or sometimes it can hurt you. So the reason you feel that, or if that object's if it's big enough and going fast enough, it can hurt you, is because it's imparting some energy to you. So, and that's called kinetic energy. The energy of motion is called kinetic energy. So we'll do an example here. A science teacher with a mass of 70 kilograms is skipping at 3 meters per second. What is his kinetic energy? So this one is a little bit easier in the sense that we only have to worry about two variables. We have mass and velocity, but we don't have to worry about gravity here. But we have to worry about a couple of different operations here. We have that 1/2 out in front, and we have to square the velocity. So let me show you what that looks like. So I always just like to start with what we know. So we know that the mass of this teacher is 70 kilograms. We know that his velocity is 3 meters per second. Okay. And then going off the formula on the left, right here, I know that I have to say kinetic energy equals 1/2, that 1/2 is important, times the mass of 70 kilograms, times the velocity. Oh, this is kind of getting messy. Let me go back a little bit here. I'm trying to write a little bit smaller so I can fit everything. 1/2 times 70 kilograms times 3 meters per second squared. Okay, so I have to square that 3 over there. That's important. So if I square the 3, if you guys don't remember squares, it's just a number times itself. So 3 times 3. So I have 1/2 times 70 kilograms. And then I would say times 9. And I'm not going to ask you guys to remember those units over there. Those are kind of meaningless units of those at this point. So now I'm just going to multiply the rest together. I square the 3, just multiply everything. 1/2 times 70 times 9. So 1/2 of 70 is 35. 35 times 9. So I come up with 315 joules, or just J. That's how we calculate kinetic energy. It's multiplication again, but we have to remember which one to square. Don't forget about that 1/2. So 315 joules. There we go. So let's talk about the conservation of energy. There's a law about energy called the conservation of energy. So the very first day you spent on energy, we talked a lot about how different forms of energy can be converted into another. For example, in order to receive power on your computer, that you get that power from the electrical outlet. That electrical outlet gets its power from a power plant, which it gets its power from coal. So it all starts with energy inside of these uh, coal. So that chemical energy has to be converted into steam energy, which is then converted into mechanical energy to drive the turbine, which makes electrical energy. So that's all different types of energy being converted from one form to another. So the conservation of energy is kind of a law that tells us what exactly happens with that energy conversion. So it says in a closed system, energy can change form, but the total energy does not change. What that really just means is that I cannot create energy. In order to drive my car, I cannot just magically drive my car. I need the chemical energy of my gasoline in order to move forward. And like in that first example that we looked at with potential energy, that pot of flowers doesn't just fall down magically. It falls down because gravitational energy is being converted into kinetic energy. So energy cannot be created or destroyed, but it can be converted from one form to another. So here's an example here. So as this cannon shoots its cannonball upward, um, the cannonball gets its initial energy from the explosion, whatever gunpowder or whatever was inside that cannon. So that explosion propels the cannonball upward, making it go up, up, up. So it's gaining potential energy as it goes up. So that chemical energy is converted into potential energy for the cannonball, and the cannonball will eventually lose that potential energy as is being falls back down toward the ground. So as it falls back down toward the ground, it loses potential energy, which is converted into kinetic energy. So, and you guys are going to look a lot about this conversion between potential and kinetic energy. But remember, potential energy, or at least gravitational potential energy, is just when something has some set height above the ground. And kinetic energy is the energy of motion. So when something falls, it loses potential energy, but it's gaining kinetic energy. So that's what the conservation of energy means, that that potential energy is not lost. It is just converted into kinetic energy. And this is an example from CK12. It says one of the Lady Spartans was fallen to the ground after dunking the winning basket. At the end of her fall, she has 960 joules of kinetic energy. If she had 60 kilograms of mass, what height does she fall from? So I'm not going to solve this problem for you, but I will set it up. So if we have somebody, instead of drawing a person, I'm just going to draw a little dot blob here. Oh, she already has her arms. I'll go ahead and finish it. Okay, so she's falling. So what are we given? Well, we know that she had, at the end of her fall, she had 960 joules of kinetic energy. And kinetic energy, remember, it just means the energy of motion. So at the end of her fall, so if this is the ground right here, she hits the ground. Hopefully she's not hurt. But this kinetic energy is equal to 960 joules. So all that kinetic energy is lost once she hits the ground. It's not destroyed, but it is lost to friction, and basically all that energy is transferred into the ground. So we're given her mass, 60 kilograms of mass. We need to know that. The question is, what height does she fall from? Well, it gives us kinetic energy, but we need to know about potential. We need to know about potential energy, because kinetic energy, remember that formula. Let me get a different color. Remember, the formula for kinetic energy does not use height. It uses mass and velocity, 1/2 times mass times velocity squared. So we could use that 960 to solve for exactly how fast she was going, but it's not asking for the speed, it's asking for what height. So we have to remember that energy is not lost or destroyed. So whatever kinetic energy she had is due to her fall. There was nothing else happening in this problem. There's no one who threw her down. There was no cannon shooting her to the ground. She fell from some kind of height. She's dunking a winning basket, so she's falling from a basketball goal. So the problem is asking about her height above the ground. So we can safely assume that the potential energy, or sorry, the kinetic energy comes from the kinetic energy comes from all that potential energy. In other words, they should be equal. According to the law of conservation of energy, the potential energy should be equal to the kinetic energy. So if we, oops, sorry, I have some glasses here almost down. So if we remember that potential energy is equal to the mass times gravity times height, we should be able to solve the problem now because we know her mass, we know gravitational constant. Now we just need to solve for her height. So this is where we have to use a little bit of algebra, because now what we need to do is we need to solve for h. So like I said, I will set this up for you. I'm not going to solve it completely, but I will set this up. So we know potential energy is equal to the kinetic energy. The kinetic energy was 960 joules. We know her mass, we know the gravitational constant, and we need to solve for the height. So I'm just going to erase this stuff over here so I can have some more room. To do some algebra on the right side. So why is my eraser still on? Here we go. So potential energy equals mass times gravity times height. And remember, we're trying to solve for height. So we're trying to solve for h. So I think you guys are at the point in algebra where you guys are solving equations. So I know that you guys are usually used to working with numbers, but we're going to work with just letters here because all of these letters represent something. So if the height is being multiplied by g and m, how can we get h by itself? What we just need to know is, well, what's the opposite of multiplication? The opposite of multiplication is division. So if we want to get h by itself, we need to divide both sides by mass times gravity. When we do that, in my next step, this will cancel mass times gravity on the right side. And so what I'm left with is potential energy, which we are given, 960 joules, divided by mass, which we are given, times g, equals the height. So if you guys get that question on CK12, I'll let you guys plug in the numbers. You have potential energy, mass, and gravity, and if you put it into that equation, you can solve for height. And that is how you would solve for height in any situation. As long as potential energy is the only source of energy, you can find the height that an object fell from, as long as you know the mass and the energy. So that's all for now. If you're watching this video on the very first day of introducing potential kinetic energy, you might not have to use these equations on the first day, but I do encourage you to come back to this video if you want to watch some examples of how to solve for kinetic energy or potential energy, or using the conservation of energy. Please feel free to come back to this video and use it later. If you have any questions, please don't be afraid to come to my Zoom sessions. I have Zoom sessions an hour every weekday, and look forward to working with you guys there. Otherwise, get a hold of me however you want. I'll talk to you later.